All right, we're going to continue with section 5.5. Get this lined up here. And this time, since we've been kind of concentrating on the graphs of logarithm functions, we're now going to turn to an analytical approach to logarithms. Basically, we've touched on this, but how do you evaluate a log by hand and eventually using technology? So, in general, we'll always start by taking our logarithm equation and thinking of it in terms of the exponential that it's associated with, because that's our best bet for actually evaluating the log. So here, if I'm thinking I would like to know what the logarithm base 6 of 36 is equal to, I identify first that the base is 6. And then what I'm asking myself is, what power do I have to use to turn that 6 into a 36? Well, I know 6 squared is 36. So the power that I would need is 2. And that means that the logarithm base 6 of 36 is equal to 2. In general, if you're being asked to show your work or justify your answer, writing down this equivalent exponential expression will usually do the trick. Notice, however, the final answer isn't 6 squared. The final answer is just the exponent. It's just the 2. All right, let's try a couple more. The log base 3 of 81. We'll identify the base as 3 and ask ourselves what power would we have to use to turn that 3 into an 81. Now, I know it's not 3 squared, right? And you may already know the answer, but I just want to point out that if you're not sure, you can always grab a calculator and try a few things. 3 to the 3rd power, that's just 27, right? 3 to the 4th power, and there it is. 3 to the 4th power is 81. So the log base 3 of 81 is 4. Again, very important. The final answer is just the exponent, just the 4. All right, how about the logarithm base 4 of 64? Our base is 4. What power would turn that into a 64? I'm pretty sure 4 cubed is 64. Again, you can check that on a calculator if you'd like. So the exponent I had to use was 3. All right, next few examples all involve having a fraction in the argument, in other words, inside the log function. So the log base 5 of 1/25. With a base of 5, what power would I have to use to get a result of 1/25? The first thing I'm going to say here is that in order to move that into the denominator, I know for sure it's going to be a negative power. I also know 5 squared is 25, so I think my negative 2 is going to do that. So, excuse me, my exponent here that I had to use was negative 2. We'll try a couple others similar to that. Here my base is 7, and I need to know what power I would have to use to make it a 1/7. Once again, the only way to get that into the denominator is by using a negative power. And 7 is just 7 to the 1st power, so I'm thinking I'm going to go with negative 1. So the exponent I would need, negative 1. All right, I got one more like that. My base here is 2, and I'm asking myself what power would give me 1/32. Once again, to move into the denominator, I'd have to use a negative exponent. And then I need to figure out 2 to what power is 32. You can do a little bit of trial and error again. 2 cubed is just 8. 2 to the 4th, still not big enough. 2 to the 5th gives me that 32. So I'm going to say 2 to the negative 5th would put that 32 in the denominator. So my exponent that I was trying to solve for is negative 5. All right. This last row here, notice that my base is larger than the argument of the log function in each of these. How does that work? Well, let's see. The base is 9, and I need to figure out what power would give me 3. Now, I know I can't use like a first or a second or third, because that's going to just make the 9 bigger. Instead, what I actually need to use here is a fractional exponent. Kind of in the back of my mind, I'm thinking, well, I know the square root of 9 is 3. And I also know the square root could also be written as the 1/2 power. So the 1/2 power is what I need, and that's the value of the logarithm. All right, let's try that again. 8 to what power gives me 2? Again, it's getting smaller, so I know it's going to have to be a fractional exponent. And kind of in the back of my head, I'm thinking, well, I know the cube root of 8 is 2. So I'm just going to think of that cubed root as a 1/3 power. And the exponent I would need is 1/3. All right, this last one combines a couple of ideas. Let's see. I have 16 as my base. I need to know what power it would take to turn that into a 1/4. Now, first of all, to put it in the denominator, going to have to be a negative exponent. But then I'm also thinking it's the square root of 16 that gives me 4. And again, square root is a 1/2 power. So I'm thinking I could go with negative 1/2. Okay. So it takes a little bit of thinking through, but definitely possible to evaluate these logarithms by hand as long as they're set out to kind of come out evenly, like these have been. All right. Talk about a couple of special logarithms. One you kind of already met just a little bit. We'll get to that in a moment. But I'm going to start up here with the logarithm base 10. Right? Because we have a base 10 number system, very often when we have a logarithm base 10, we simply don't write the base at all. So if you don't see a base, it automatically means base 10. And we actually just call that the common logarithm. So if I have the logarithm of 1,000, that's automatically the logarithm base 10 of 1,000. My base is 10. What power would I need to get 1,000? Well, I know 10 cubed is 1,000. Right, remember that little memory aid that whatever power you put on the 10, that's how many zeros you get? So the log of 1,000 is 3, third power there. All right, the log of 0.01. I know it's the log base 10 because the base wasn't written. And I think I'm going to be better off if I think about that decimal as a fraction instead. 0.01 is 1/100th. And I could write 1/100th as a fraction. And then when I say, hey, 10 to what power is 1/100th? I did have to go into the denominator, so a negative exponent. And 10 squared is 100. So my missing exponent here is -2. All right, the last example here the log of 23 could be written as the log base 10 of 23 if I wanted to, right? When the base isn't written, it's always automatically 10. And so what I'm asking is 10 to what power gives us 23? For the first time, I don't think we're going to be able to figure this out by hand. I'm sure you already realize this, but of course if I took 10 to the first power, it would just be 10. And if I took 10 to the second power, it would be 100. And 23 is somewhere in between there. So it must be like a fractional or a decimal power, somewhere between 1 and 2. That's not something I can do by hand. So we're just going to go ahead and use the calculator. You can use Desmos just as easily. On the calculator, of course, we have our log button right down here next to the 7 key. In Desmos, you just type log. I'm going to use that log of 23. And notice it automatically gives me the common log, base 10. And if I round that to, say, 3 decimal places, it's about 1.362. All right, so that's the common logs, logs base 10. There's one other special case, and we actually saw this briefly when we were graphing. It's the natural log. The natural log is the one where we use the base e, approximately 2.718. Again, the name is natural log, and that is an ln. Sometimes people look at it and they think it's in, but it's not. It's lowercase l, ln, for logarithm natural, or the natural logarithm. Okay. It really means a log base e, although truthfully in math you really never see anybody write it that way. They always abbreviate it as the ln, or natural log. So we're going to find some natural logs, and these we typically need a calculator to help us with, since of course that weird base is going to be hard to work with. Okay. So your natural log key is right below the log base 10 or common log key. It's right here. Again, in Desmos you can just simply type ln and it will understand. So if I want the natural log of 3, it's about, did it tell me what to round to? I'm going to go 3 decimal places. 1.099. And the natural log of 58 is about 4.060. And our last one over here, the natural log of 0.4 is about negative 0.916. So natural logs typically have to be done in the calculator. All right, so now that we kind of have a feel for how to evaluate logarithms, let's talk a little bit more about the properties that a logarithm function has to follow. First of all, what kinds of numbers can act as the base of logarithm functions? The answer to that is most positive numbers. The base b must be positive. The problem with a negative base is if you tried to apply a fractional exponent, like say 1/2, if I had a negative base like -4, and I wanted to raise it to the 1/2 power, that'd be the square root of -4, and that's going to get us into imaginaries. So we're going to avoid that by requiring that the base is positive. Even amongst positive numbers, there's one base that's never used. B is not equal to 1. If you think about it, 1 is a kind of a useless base because 1 to any power is still 1. It doesn't really get us anywhere. Any positive number other than 1 can be used as a base, but I'm going to tell you for the purposes of this class, we're basically going to stick with our bases larger than 1. All right, what about in the argument? What numbers can be in the argument of the log function? When I say argument, talking about right there. What am I taking the logarithm of? Well, let's see. If I'm talking about the argument, I'm talking about the x values, the inputs. And as it says in the little note, if I'm talking about all the inputs, I'm really talking about the domain of the function. If you remember back to last time when we were graphing, right, that was the typical graph of a logarithm function. And all those x values are bigger than 0, right? In fact, they're never even equal to 0, they're just bigger than 0. So by considering the graph, I'm going to say x has to be larger than 0, or in other words, anything between 0 and infinity could be in the argument. All right, for the rest of these, we're going to assume we have an allowable base, so a positive number that's not 1. What can we say about the log base b of 1? Let's see here. We're saying b to what power would give us 1? Well, no matter what b is, if I raise it to the 0 power, I'll always get 1, right? Anything to the 0 power is 1, except for 0 itself. So my exponent here is 0. Doesn't matter what base, the log of 1 is 0. All right, what about the log base b of b? Well, that's really saying with a base of b, what power would it take to get a result of b? That's just a first power. b to the first is b. So my exponent here would be 1. And this last one, the log base b of b to the n power. So my base is b. I want to know what exponent would I have to use to turn that into b to the n. Well, just by comparing those two sides, we got the same base. Therefore, in order to be equal, we'd have to have the same power, right? It's going to look a little weird, but I'm basically saying that b to the n is b to the n. So my missing exponent is n. That statement there is particularly important because you can see the inverses. Right? The exponential base b and the log base b are inverse functions, so they kind of do and undo, and what's left is just that n up there. All right, let's practice some of that information just a little bit. Log base 6 of 1. 6 to what power equals 1? Well, 6 to the 0 power is 1. So I'll get 0 here. The log base 5 of negative 25. Remember that log graph, right? X values can't be negative. That graph only existed on the positive side. So negative 25 is not in the domain, meaning that logarithm is not a real number. In this class, we will not talk about any logs that aren't real numbers, so that's all you have to say. I'm not going to come back later and say, hey, do you know how to write that as an imaginary number or something? Not going to do that. We're just going to say it doesn't work, it's not in the domain, it's not a real number. All right, the log base 4 of 4. 4 to what power equals 4? That's going to have to be a first power. Log base 16 of 0. Once again, 0 is not in the domain. We know that, again, that log graph, remember what it looks like, never quite touches x equals 0. 0 is not in the domain, so this does not exist. You might have noticed a subtle difference in the way I answered these, and I'm not going to hold you responsible for this, but I am going to mention that these truly are different things mathematically. The log of a negative number, if you start playing around with a lot more with complex numbers, imaginary numbers, eventually you'll learn that there are some definitions there. But the log base anything of 0 never exists. It's not a real number, it's not an imaginary number, it simply doesn't exist. Like I said, subtle difference, I'm not really holding you responsible for it, but that's why I wrote those differently. All right, the log base 7 of 7 to the 8th power. So 7 to what power? Gives us 7 to the 8th power. Clearly that would have to be an 8. Alternatively, I could recognize the inverse functions here. The log base 7 and the exponential base 7 are inverses. When you have a composition of inverses, what do you get out? Well, just what you put in this case, the 8. All right, with f, I've got a base of 2. What power would it take to get me 1? The 0 power. All right, these last few are natural logs. So I can always think of them as, hey, that's actually a base of e, even though it's not written. So here I'd be saying e to what power gives me 1? Well, again, anything to the 0 power is 1. So that's going to have to be 0. The natural log of e to the 4th. Again, that's really a base e. So what I'm saying is e to what power equals e to the 4th power. And clearly that would have to be 4. This, by the way, is another example of inverse functions. Since the natural log is the log base e, it's the inverse of the exponential function base e. And you can just think do and undo, which would have left us the 4 that way also. All right, one more here. The natural log of 1 over e to the 7th. Again, I know that's base e. So that says e to what power gives me 1 over e to the 7th. In order to see the correct answer to this one, I'm going to rewrite that. I'm going to say I could move that up into the numerator by changing the sign on the exponent. On top, it would be e to the negative 7th. And now I can clearly see that that has to be negative 7. All right, that brings us to the end of section 5. Where are we? 5.5, yeah. We'll see you for 5.6 next time.